Alright, in this video, we'll be solving the CIE A-Level Math, October-November 2024, paper 61, and this is also exactly the same as the paper 63, so you can watch this one if you're here for paper 63 as well. This is probability and statistics 2. If you're feeling anxious, overwhelmed, or unsure where to start, then I've created a complete course that streamlines everything with step-by-step videos, interactive quizzes, and an exclusive student community to keep you on track. You can get access to it by clicking the first link in the description. Otherwise, like the video, subscribe, and let's dive right in. Number 1. The heights of a certain species of deer are known to have a standard deviation of 0.35 meters. A zoologist takes a random sample of 150 of these deer and finds that the mean height of the deer in the sample is 1.42 meters. Part A. Calculate a 96% confidence interval for the population mean height. Okay, so we are dealing with a large sample of reindeer, 150. And so it means that the formula we can use, even though this is not normally distributed, is x bar plus or minus z sigma over root n. Okay. And in this case, our x bar will be our mean height. So the mean height of the sample, x bar is 1.42. And then to get z, we want a 96% confidence interval. So it means we're going to have 96% in the middle. This here is going to be 96%. I'll write it as 0.96. So this means either side we're going to have 0.02 and 0.02 so that it all adds up to 1. So it means our z value here is going to be arc phi of 0.96 plus 0.02, so that's 0.98. This is going to be our z. So use your normal distribution tables and read it in reverse. So z is 2.054 and our sigma has been given as 0.35, and our n is our sample size, which is 150. So we can find our interval. It's essentially going to be 1.42 plus or minus z, which we said is 2.054, multiplied by sigma, which is 0.35, divided by the square root of 150. And so let's punch this into the calculator. I'll start with the lower limit, 1.42 minus 2.054 multiplied by 0.35 over the square root of 150. And this gives us, that's 1.36 to 3 significant figures. And let's do the upper bound. Upper bound will be 1.48 to 3 significant figures. Part B, Ube says that 96% of deer of the species are likely to have heights that are within this confidence interval. Explain briefly whether Bube is correct. So remember, when we're talking about confidence interval, we are focused on our population parameter. So in this case, we're focused on our population mean. So when we say we want a 96% confidence interval, we are saying that there's a 96% chance that our true population mean lies within this interval. That's what that means. And here Bube seems to be talking about the actual individual deer of the species. But when we talk about confidence interval, our focus is on the mean, whether our mean lies within this confidence interval. So to say that 96% of deer of the species are likely to have heights that are within this confidence interval, we don't know. That's not what we're interested in. We are focused on the mean. So no, Bube is not correct. Bube is not correct. Our confidence interval is about the mean, or is focused on population mean. on population mean. Whilst our bay here is focused on the individual deers. Number two, the masses in kilograms of small and large bags of wheat have the independent distributions, normal distribution with mean 16.0 and variance 0.4. And the large bags also have a normal distribution with mean 51.0 and variance 0.9. Find the probability that the total mass of 3 randomly chosen bags is greater than the mass of one randomly chosen large. So we are given small and large bags. So the small bags follow a normal distribution with mean 16.0 and variance 0.4. And our large bags follow a normal distribution with mean 51.0 and variance 0.9. And what we want is the probability that 3 randomly chosen small bags. These are independent observations of the same random variables. So this is a sum. It's going to be S1 plus S2 plus S3. And this must be greater than the mass of one randomly chosen large bag. So greater than L. Okay. So whenever you see 3 randomly or n randomly chosen, this is independent observations, independent observations, how do you spell observations? Observations of the same random variable, of the same random variable, i.e. this is a sum, it is not a multiple. A multiple is when they say this has doubled, this has tripled, this has quadrupled. But if they say in randomly chosen bags, in randomly chosen objects, we are looking at independent observations of the same random variable, which is a sum. And as you should know by now, the key difference becomes in calculating your variance. So the variance here is going to be equal to, this is the var of, we're saying nx, let me write it properly. The var of nx is going to be equal to n var x. All right. If it's a sum, that's the key here. It's not n squared. If it was a multiple, then it would be n squared. The mean should not be a problem. The expectation of x, because it's the same for both of them, is just going to be nex. Anyways, back to the question. So this is what they want us to find. So I'm going to move our L to the left so that we have the probability of S1 plus S2 plus S3 minus L, and this is greater than 0. And so that we don't have to keep writing this long expression, I am going to call this D. So D is equal to S1 plus S2 plus S3 minus L. And let's find the mean and variance of D. So the mean of D is going to be the expectation. Okay, so this first 3 here is a sum. So to find the expectation of these 3, it's n times the expectation of S of x. So in this case, it's 3 times the expectation of S, which is 16, minus the expectation of L, which is 51. So the expectation of D is equal to, that is 3 multiplied by 16 minus 51, and this gives us a negative 3. And we also want the variance. The variance of D is going to be equal, it's n by x. So it means for these first 3, it's going to be 3 multiplied by the variance here, which is 0.4. And then we want the variance of L. Remember, variances are always added. So even though it says minus L, we are going to add, because at the end of the day, it's just negative 1 squared times the variance, which is 0.9. So var of D is equal to, that is 3 times 0.4 plus negative 1 squared times 0.9, and this gives us 2.1. Now, because D consists of S and L, which both follow independent normal distributions. We can therefore they say that D follows a normal distribution with its mean being -3 and its variance being 2.1. And we want the probability that, remember this whole expression is D, so the probability that D is greater than 0. And we can standardize. So that would be Z is greater than 0 minus -3, so 0 plus 3, over the square root of our variance, 2.1. And so that's the probability that Z is greater than 3 over 2.1, or the square root of 2.1 rather. And so that's 2.070 to 3 decimal places. So to get this area, it's going to be 1 minus 5 of 2.070. So that's 1 minus 5 of 2.070 is 0.9808. Therefore, our final answer should be 1 minus 0.9808, which is 0.0192. Number 3. The times t minutes taken by a random sample of 75 students to complete a test were noted. The results were summarized by the summation of t is 230 and the summation of t squared is 930. Part A. Calculate unbiased estimates of the population mean and variance of t. Alright, so let's start with the unbiased estimate for our mean. That's going to be the summation of t divided by n. So mu hat is equal to summation of t is 230, and this is divided by our sample size 75. And so you get that mu hat is equal to, this is 230 over 75, which is, if we're giving it to 3 decimal places, or 3 significant figures rather, 3.07. And then unbiased estimate of our population variance is going to be 1 over n minus 1 times the summation of t squared minus the summation of t squared over n, and then we close our bracket. So that's s squared is equal to 1 over n minus 1, so 75 minus 1, which is 74, times the summation of t squared, which is 930, minus the summation of t, which is 230, and this is squared, and this is over n, which is 75. All right, so let's punch this into the calculator. That's 1 over 74 times 930 minus, that's 230 squared over 75, and this gives us 3.0. In fact, let me first give it as an exact value, and then I will simplify it. So this is 337 over 111, which simplifies to 3.04. Okay, and that's our final answer. You should now assume that your estimates from part A are the true values of the population mean and variance. Part B, the times taken by another random sample of 75 students were noted and the sample mean t bar was found. Find the value of A such that the probability of t bar being greater than A is 0.234. Alright, so because n, our sample size, is equal to 75, this is greater than 30, using CLT, since we don't know the distribution of t, our population, we can then use CLT to say that our sample mean follows a normal distribution, because it satisfies the condition that n should be sufficiently large enough, or in other words, n should be greater than 30. And our mean is going to be our estimate here. I will use the exact value, 230 over 75, and then our variance, 337 over 111, but this has to be divided by the sample size, which is 75. Okay, I should make the brackets bigger. In fact, maybe let's not use exact values. Let's use just so that it's more readable. We'll use about 4 decimal places or so. 230 over 75, that's going to be 3.0667 for our mean, and then our variance is going to be 337. Remember, the reason I've divided by n is because it's supposed to be sigma squared over n when you're finding the variance of your sample mean. And in this case, our n is 75. Our sigma squared is the estimate from part A. So this is 337 over 111 over 75, which gives us 0.04048. Okay. And we want to, I should not be using x, I should be using t. Okay, because our random variable, our population is coming from t, so it means the sample mean is t bar. So that should be x. That shouldn't be x, it should be t bar. Okay, so t bar. All right, and we want to find the value of a such that the probability that t bar is greater than a is 0.234. So we have the probability that t bar is greater than a is equal to 0.234. If we standardize, this would be z is greater than a minus what's our mean? 3.0667 divided by our standard deviation, so the square root of this number here, the square root of 0.04048, and the probability would still be the same, 0.234. So what we want to do is to find a. And how we're going to do this is we want to find the z value that corresponds to this probability. So let me just rewrite this or replace this with this z value and say this should be 0.234. And we want to find the z value that corresponds to this probability. So just to visualize what we're looking at, we've got our bell curve and 0 is somewhere there. The probability that z is greater than z is round about 0.23, so close to 20% is going to be on this side, z, and this area should be 0.234. This is the area greater than z, it's 0.234. So we want to find what the z value is for this probability, but we know that our tables only start from 0.5 for areas, so we can't use 0.234 to find our z value. So we're going to say 1 minus 0.234 because total area under our bell curve is equal to 1. So the unshaded region is going to be 0.766. And so if we say arc phi of 0.766, this is going to give us the z value that we're looking for. So z is going to be arc phi of 0.766. And if you read it from your tables, you should get that z is equal to 0.726. And remember here, we just simply substituted this whole expression with z. So in other words, what we're saying is that z is equal to that expression. Z is a minus 3.0667 over the square root of 0.04048. So it means that our z, we now know what it is. It means that 0.726 is equal to a minus 3.0667 over the square root of 0.04048. All right, and so now let's solve for a. We can say that 0.726 multiplied by the square root of 0.04048 is equal to a minus 3.0667. So a is going to be equal to, that's your 0.726 multiplied by the square root of 0.04048 plus 3.0667. So a is equal to, let's punch that into the calculator, 0.726 times the square root of 0.04048, and this is plus 3.0667. 667. That gives us that A is 3.21, correct to three significant figures. I don't know if they specified. No, they didn't. So we can give it to three significant figures. A is 3.21. Number 4, a random variable x has probability density function f defined by f of x is equal to a over x squared minus 18 over x cubed when x is between 2 and 3 inclusive and it is 0 otherwise. Where a is a constant, part A show that a is 27 over 2. So using one of the properties of probability density functions, we can find A. The property we want to use is that the total area under our PDF is going to be equal to 1. So if we integrate from our lower limit to the upper limit, so from 2 to 3, and we integrate A over x squared minus 18 over x cubed with respect to x, the area we get should equal to 1. So let's do that. I'm just going to, before we integrate, I'm just going to bring our x squared to the numerator and our x cubed to the numerator. So we're integrating from 2 to 3, and we're integrating ax to the negative 2 minus 18x to the negative 3. With respect to x, this is equal to 1. All right, so let's integrate now. So ax to the negative 2, add 1 to the power, that becomes ax to the negative 1, divide by negative 1, so that's just negative ax to the negative 1. Then we've got negative 18x, add 1 to the power, that becomes negative 2, then divide by this negative 2. And our limits are from 2 to 3, and this is equal to 1. So I'm just going to write it on the side. We've got negative a, this x to the negative 1. If we take it back to the denominator, it just becomes an x. And then we've got minus 18 over minus 2, so that's positive 9. And I'm taking the x to the negative 2 back to the denominator, so it's x squared. And this is from 2 to 3 is equal to 1. All right, don't confuse this 9 and the a. That's an a. Okay, so now let's substitute in our limits. We'll start with the upper limit. That's going to be negative a over 3 plus 9 over 3 squared minus negative a over 1 plus 9 over 1 squared. And this should all equal to 1. All right, so let's simplify. We've got negative a over 3, and this is 9 over 9, so that's just plus 1, minus, that's just minus a, and this is just plus 9. This is all equal to 1. So we've got negative a over 3 plus 1 minus minus a, so plus a minus 9, and this is equal to 1. Let's simplify like terms. We've got a minus a over 3, so that's 2/3 a. And then we've got 1 minus 9, which is minus 8, and this is equal to 1. So we get that 2/3 a is equal to 9. And so if you multiply both sides by 3 over 2, 3 over 2, you're going to get a is equal to 9 times 3 is 27, 27 over 2, which is exactly what we're trying to prove. So part B says, show that the expectation of x is equal to 27 over 2 ln 3 over 2 minus 3. So the formula for mean is the integral from the lower limit to the upper limit. So in this case, that's from 2 to 3 of x, f of x with respect to x. All right, so that's going to be the expectation of x is equal to 3x multiplied by, now remember that we said a is 27 over 2, so I can write that part as 27 over 2x squared, like that, okay? And the other part is minus 18 over x cubed. All right, so that's 27 over 2x squared minus 18 over x cubed. Is that correct? Yes. And this is with respect to x. So let's multiply through and simplify our integral. We're integrating from 2 to 3. Then the x and the power 2 will cancel out there, so that you've got a 27 over 2x minus where the x and the power 3 cancel out, so that you've got a 2 here. So it's going to be 18 over x squared, and this is with respect to x. So the x here, we can leave it on the denominator, but this x squared, we need to move it up to the numerator, so that we're integrating from 2 to 3, and we're integrating 27 over 2x, and this is going to be minus 18x to the negative 2. This is all with respect to x. So let's finish it off on the side. If you integrate 27 over 2x, that is going to be 27 divided by 2, and then we've got ln 2x. And then if we integrate this part, that's negative 18x, add 1 to the power, you get a negative 1, and divide by this, negative 1. And our limits are from 2 to 3. So let's simplify. We've got 27 over 2 ln 2x, and this becomes positive 18 over x. From 2 to 3, we can substitute in our limits. We'll start with the upper limit. So that's 27 over 2 ln 2 times 3 minus, or plus rather, 18 over 3. And then we'll do the lower limit. So 27 over 2 ln 2 times 2 plus 18 over 2. All right, so let's simplify this. So that's going to be 27 over 2 ln 6 plus 18 over 3, that's 6, minus, we've got 27 over 2 ln 4, 27 over 2 ln 4, that's 18 over 2, which is 9. All right, so that's 27 over 2 ln 6 minus 27 over 2 ln 4 plus 6 minus 9. All right, what are we trying to get to? 27 over 2 ln 3 over 2. Okay, it's on the cards. So this is 27 over 2 ln, since these two logarithms are subtracting, it becomes 6 over 4. 6 over 4, and then we've got 6 minus 9, which is minus 3. So that's just 27 over 2 ln 3 over 2 minus 3. And I believe this is exactly what they wanted. Yes. Number 5. The lengths in centimeters of worms of a certain kind are normally distributed with mean mu and standard deviation 2.3. An article in a magazine states that the value of mu is 12.7. A scientist wishes to test whether this value is correct. He measures the length, x centimeters, of a random sample of 50 worms of this kind and finds that the summation of x is 597.1. He plans to carry out a test at the 1% significance level of whether the true value of mu is different from 12.7. Part A. State with a reason whether he should use a one-tailed or a two-tailed test. So with a one-tailed test, we are testing for a definite decrease or a definite increase. Okay? If they have not specified whether we're testing for an increase or a decrease, it becomes a two-tailed test, because a two-tailed test, you're just checking whether to see your mean is different or your mean has changed. You don't specify that you're testing for a decrease or an increase. So we can say that two-tailed test, because he wants to test for a difference in mu. He wants to test for a difference in mu. And then part B says carry out the test. Alright, so I'm just going to define our random variable so that we know what even we are worried about. This is length in centimeters of worms, okay, of some worms, and we know that they are normally distributed. So X follows a normal distribution with mean mu and standard deviation 2.3, 2.3 squared. Now we need our hypothesis H naught. H naught is that mu has not changed, mu is still the same, so that would mean mu is 12.7. And then H1 is that mu is different, so mu is not equal to 12.7. And assuming H naught is true, we can say that X bar follows a normal distribution with mean from H naught, which is 12.7. And our variance is going to be 2.3 squared over our sample size. And what is our sample size? It uses a sample of size 50. All right. And so essentially what we are looking at, how much space do we have? Okay, let me do it on the side. We've got a bell curve and our zero is going to be here. This is Z. Our zero is going to be there, and we want a two-tailed test. What is our significance level? Our significance level, 1% significance level. So we have to share this 1% on either side. So instead of this being 0.01, that's 1%, right? It's going to be 0.005. That is tiny. 0.005, such that this middle area is 0.99. And so we need to find the corresponding Z values. So that's going to be Z is ACPhi of 0.995, which will be in the critical values table at the very bottom of the page with your normal distribution tables. So Z is 2.576. This means that this is 2.576. It's 2.576. So we can create a rejection room, because the shaded region, the area we've shaded, is the region in which we're going to reject H naught. So we can say that reject H naught if our Z, the Z that we end up calculating using the information from Bro's sample, from the scientist's sample, right? If we find that that Z is within these shaded regions, then we reject H naught. So if Z is, this should be negative because it's less than 0. If Z is less than negative 2.576, or Z is greater than 2.576. Alternatively, you could write this as the modulus of Z is greater than 2.576. All right, but both work. So now we need to calculate that Z, and then we'll compare it to see if it is within that shaded region. So Z is going to be X bar minus mu over sigma over root n. So Z is equal to, what is our X bar? The X bar is going to be the mean that you get from the random sample that was taken by the scientist. And they gave us the summation of X instead, so they want us to calculate it by ourselves. X bar is going to be equal to the summation of X over your sample size. So X bar is equal to 597.1 divided by our sample size, which is 50. So we get that X bar, our test statistic, is 597.1 over 50. That is 11.942. So it becomes 11.942 minus mu being 12.7. and this is all over the square root of this sigma over root n, so just 2.3 over root 50. And so we get that z is equal to, this is 11.942 minus 12.7 over 2.3 over root 50. And this gives us negative 2.330. Let's check, where would negative 2.330 be? It would probably be somewhere here, right? This is clearly not in the rejection region. So we're saying negative 2.330 is greater than this value here, negative 2.576. So we do not reject H naught. Do not reject H naught. And now we have to conclude in context. We were testing to see if there is a difference, and we do not have enough evidence to say that there is a difference. So we can say that there is not enough evidence. There is not enough evidence at the 1% significance level, 1% sig level to suggest that, let's just see how they worded it. A scientist wishes to test whether this kind of whether the true value of mu is different. Okay, to suggest that the true value of mu, the true value of mu is different to 12.7. All right, and this would be our final answer. Number 6. The numbers of customers arriving at service desks A and B during a 10-minute period have the independent distributions Poisson with lambda 1.8 and Poisson with lambda 2.1 respectively. Part A. Find the probability that during a randomly chosen 15-minute period more than 2 customers who arrive at desk A. So let F be the random variable's number of customers arriving at desk A per 15-minute period, or in a 15-minute period, 15-minute period. So F is going to follow a Poisson distribution. What is lambda? We know that at desk A for a 10-minute period, lambda is 1.8. What about for a 15-minute period? It's going to be 15 over 10 multiplied by 1.8. So that's 15 over 10 multiplied by 1.8. So our lambda will be 2.7. All right. And we want to find that more than 2 customers will arrive. So probability that F is greater than 2. We can write this as 1 minus the probability that F is less than or equal to 2. So that's 1 minus e to the negative. Here we're taking what? 0, 1, and 2. So e to the negative lambda is 2.7. And if it's 0, we just have a 1. And if it's 1, we're going to add lambda. And if it's 2, it's going to be lambda to the 2 over 2 factorial. All right, so let's just punch this into the calculator. 1 minus e to the negative 2.7 times 1 plus 2.7 plus 2.7 squared over 2 factorial. And this gives us 0.506, and that is our final answer. Part B says, find the probability that during a randomly chosen 5-minute period, the total number of customers arriving at both desks is less than 4. So let's define our random variable t as the random variable total number of customers arriving at both desks per 5 minutes. So we can say the total in a 10-minute period for A and B is going to be 1.8 plus 2.1, which gives us what? 1.8 plus 2.1 gives us 3.9. 3.9. This is total per 10 minutes, right? We want per 5 minutes, so we have to divide this by 2. We have to divide this by 2. We want 5 out of 10 by 3.9. That gives us 1.95. It means our lambda is going to be 1.95. So T follows a Poisson distribution with lambda 1.95, and we want the probability that T is less than 4. So the probability that T is less than 4, this means we're going to take 0, 1, 2, and 3. Okay, so that's e to the negative 1.95 times 0 is going to be 1 plus 1 is going to be just lambda, so 1.95. 2 is 1.95 squared over 2 factorial plus 3 is 1.95 cubed over 3 factorial. So the probability that T is less than 4 is equal to, let's punch that into the calculator, that's e to the negative 1.95 times 1 plus 1.95 plus 1.95 squared, and this is over 2 factorial plus 1.95 cubed over 3 factorial, and this gives us 0.866, and that's our final answer. Part C says an inspector waits at desk B. She waits long enough to be 90% certain of seeing at least one customer arrive at the desk. Find the minimum time for which she would wait, giving your answer correct to the nearest minute. Okay, so let's define our random variable M as the random variable. Number of customers arriving at desk B, because our focus here is desk B. The inspector is waiting at desk B. At desk B per, and here we don't know how long she waits, so we're just going to write this as t minutes per t minutes. That's in fact what we want to find out, per t minutes. And we can say that M follows a Poisson distribution with lambda being. So how we can do this is to say that we know that at desk B, for a 10-minute period, it's 2.1. At desk B, for a 10-minute period, it's 2.1. So what about for a 1-minute period? It's going to be a tenth of 2.1. So a tenth of 2.1, that's going to give us what? This is 0.21. This is now per minute. So that means if we want per t minute, it's just going to be 0.21 times t. So in other words, our lambda here is going to be 0.21 t. Okay, because we don't know exactly what our minutes are. Our minutes are t, and they're just going to be multiplied by per minute. Because if this was per 2 minutes, it would be 0.21 times 2. And we are told that she waits long enough to be 90% sure. Okay, so we're going to say that long enough to be 90% sure, whatever probability we have here is going to be greater than 90, greater than or equal to. She wants to be at least 90% sure, so 0.90, and then of seeing at least one customer arrive at the desk, at least one. So that means our customer here greater than or equal to 1, M is greater than or equal to 1, means at least one customer arrives at desk B. And so to find this probability here, we can rewrite this as 1 minus the probability that M is less than 1, is greater than or equal to 0.90, which is the same as just saying 1 minus the probability that m is 0, greater than or equal to 0.90. And so we get that this is 1 minus e to the negative lambda. What is our lambda? Our lambda is 0.21 t. And this is greater than or equal to 0.90. So now we need to solve for t. So this becomes e to the negative 0.21 t is less than or equal to, because we're moving our lambda this side, is less than or equal to 1 minus 0.90. So e to the negative 0.21 t is less than or equal to, that's 0.10. Okay, and then we can take the natural logarithm on both sides, ln, and so the ln and the e cancel out. You end up with negative 0.21 t is less than or equal to ln 0.10. And then we're going to divide both sides by negative 0.21. If you divide by a negative, then it's going to flip your sign. So this becomes ln 0.10 over negative 0.21. So t is greater than or equal to, this is going to be ln 0.10 over negative 0.21. This gives us t is greater than or equal to 10.96. And so t, the minimum value for t, is t an integer. The minimum time she would have to wait is going to be 11 minutes, right? T is 11 minutes. That's the minimum time she would have to be wait to be 90% confident that one customer will arrive at disk B. So t is 11 minutes, and that's our final answer there. Number 7, the number of accidents per year on a certain road has the distribution Poisson with lambda lambda. In the past, the value of lambda was 3.3. Recently, a new speed limit was imposed, and the council wishes to test whether the value of lambda has decreased. The council notes the total number x of accidents during 2 randomly chosen years after the speed limit was introduced, and it carries out a test at the 5% significance level. Part A, calculate the probability of a type 1 error. So if we're to define our random variable here, or they've defined it for us, x is the number of accidents for 2 randomly chosen years. And so that would mean x would follow a Poisson distribution with 2 times lambda, because lambda is for a year. So x would follow Poisson distribution 2 times lambda. So 2 lambda would have a value of 2 times 3.3, which is 6.6. Okay, so we're saying that x follows a Poisson distribution of 6.6. And so this would mean you don't need to put your now and alternative hypothesis. Yeah, in fact, they're needed in part B, but just so that we understand what's going on, we're saying that either our lambda is 6.6, this means that it hasn't changed, or lambda has decreased, so it means it's less than 6.6. And so we're carrying out our test at a 5% significance level. So if we want the probability of a type 1 error, it's the probability for us rejecting H naught. We reject H naught if the probability that X is less than, in this case, we take the sign of H1 and we also include the critical value. So the probability that X is less than or equal to C is less than the significance level as well. So it's less than 0.05. So this gives us our rejection region, and essentially, and all a type 1 error is, it's just the probability of being in the rejection region. So what we can do is we can use trial and error to find our rejection region. For example, we can start by evaluating the probability that X is less than or equal to 2. So that's going to be equal to e to the negative, our lambda is 6.6, 6.6, and then we've got 1 plus, that's 6.6, plus our 6.6 squared over 2 factorial, and let's see what this gives us. Less than or equal to 2 is equal to, You punch that into the calculator, e to the negative 6.6 multiplied by, that's 1 plus 6.6 plus 6.6 squared over 2 factorial. That gives us 0.03997. Okay, this is less than 0.05, but we need to check the next number 3, because that might also be less than 0.05, because we want to include all the values that are less than 0.05. So we'll try x is less than or equal to 3. That's e to the negative 6.6, 1 plus 6.6 plus 6.6 squared over 2 factorial, and this is plus 6.6 cubed over 3 factorial. So that's the probability that x is less than or equal to 3 is equal to, you punch that into the calculator, you get 0.105. Okay, so this is in fact greater than 0.05. So that means 3 would now be outside of the rejection region. So essentially, if you wanted to visualize it, we are probably looking at something that looks like this. Let's say we've got, say 1 is here, 2 is here, 3 is here. Our cutoff point would probably be somewhere here. And this area here to the left, this is 0.005. That's going to be our rejection region. But remember, because we're dealing with a discrete distribution, it essentially just means our rejection region starts at 2, and then the next value would be 1, and the next value would be 0. So it means our rejection region is x is less than or equal to 2, because the probability that x is less than or equal to 2 is equal to 0.03997, which is less than 0.05. And this also happens to be, so this is the rejection region, and this becomes the probability of a type 1 error. So you can say that the probability of a type 1 error is equal to, let's round that off to 3 significant figures, so 0.0400. All right, and then part B, given that x is 2 carried out the test, as you can see with the diagram that I've drawn here, x is 2 is in the rejection region. So you just say our rejection region is x is less than or equal to 2, and 2 is less than or equal to 2, so reject h naught. And conclude in context. What is our context? We are arguing that lambda has decreased. Oh, by the way, I forgot. We need our hypothesis. You don't need your hypothesis for part A, but you need to write down your hypothesis in part B for sure. You get marks for that. Okay. And then we say reject H naught. And we're testing to see whether lambda has decreased. So we can say that there is sufficient evidence. There is sufficient evidence at the 5% significance level to suggest that the value of mu, the value of lambda, not mu, the value of lambda has decreased. Okay, and that will be our final answer. Part C says the council decides to carry out another similar test at the 5% significance level using the same hypothesis and 2 different randomly chosen years. Given that the true value of lambda is 0.6, calculate the probability of a type 2 error. So we found that our rejection region was x is less than or equal to 2. So a type 2 error is when we do not reject H naught. So in other words, the probability of being outside the rejection region, the probability that X is greater than 2. However, it always comes with a correction in our population parameter. And so they give us the corrected value or the true value of lambda in this case. So given that lambda is equal to 0.6. But I want you to be very, very careful here, because if you remember going back here, when we were doing our test here, we used 2 lambda, not just lambda. So they've corrected lambda, but you have to be aware that we are dealing with 2 years, not 1 year. So you want to multiply that value by 2. So in fact, what you're looking at is x follows a Poisson distribution with your lambda being 0.6 times 2, which is 1.2. Okay. And so we want the probability that x is greater than 2. So maybe rather than saying that this is 0.6, we're saying that this is 1.2. So probability that x is greater than 2, that's going to be 1 minus the probability that x is less than or equal to 2. So that's 1 minus e to the negative 1.2 times, we want 0, 1, 2. So 1 plus 1.2 plus 1.2 squared over 2 factorial. And that's going to be, punch that into the calculator. This is 1 minus e to the negative 1.2 times 1 plus 1.2 plus 1.2 squared over 2 factorial, which gives us that the probability of our type 2 error is equal to 0.121. And that will be our final answer. Part D says, using lambda is equal to 0.6 and a suitable approximating distribution, find the probability that there will be more than 10 accidents in 30 years. All right, so let's create a new random variable, and we can call our random variable y. Let y be the number of accidents in a 30-year period. In a 30-year period. So y follows a Poisson distribution with lambda being, for 1 year, we expect lambda to be 0.6. So for 30 years, it's going to be times 30. So 30 times 0.6, that gives us 18. So lambda is 18. And since lambda is equal to 18, which is greater than 15, we can use a normal approximation. Normal approximation to the Poisson distribution to Poisson. So we can say that y follows a normal distribution with our mean being lambda and our variance being lambda. So y follows a normal distribution with mean 18 and variance 18. And we want to find the probability that y is greater than 10, greater than 10. But remember that this question was defined under discrete conditions. And we have moved to a continuous distribution. So we have to apply continuity correction. So if we're taking greater than 10, under a continuous distribution, 10 represents any value from 9.5 all the way up to 10.5. So if we're taking greater than 10, we don't want to include 10, and we're moving that way. So it means it's going to be greater than the upper bound, yeah? So greater than 10.5. So this becomes the probability that y is greater than 10.5. And we can go ahead and standardize. So z is greater than 10.5 minus our mean, which is 18, divided by our variance, or the square root of our variance. So square root of 18. So that's the probability that z is greater than, that is 10.5 minus 18 over the square root of 18, which gives us negative 1.768. All right, which we can write as, this is the same as the probability that z is less than 1.768. So that's just going to be phi of 1.768. And so let's read off the value of phi of 1.768 from the normal distribution tables. It gives us 0.9615. So therefore our final answer would be 0.962. Right, and that is the question and also the full paper. So I hope you found that breakdown useful. If you did, please share this video with others who you think might also benefit from it. Otherwise, like the video, subscribe, and comment down below what paper would you like to see me break down next. Bye bye.